Yeah, as Patrick says, so today we will cover a real case study about all-flash implementation with xiRAID and Lustre. And then Markus will give us some more information, not just about the case study, but also about best practice to implement our technology together with Lustre. Since MEGWARE developed a lot of expertise in this area. And then we will look at IO 500 results. And at the end, we will also look at how to make this solution highly available, able to survive also a server node failure. Okay, so let's start from the why. Why do we need a RAID engine specifically for all-flash, specifically for NVMe? I'm pretty sure you are very familiar with RAID technology. It was not invented by Xinnor. It has been in the market for many years. And actually, you can do RAID in two ways. You can do hardware RAID or you can have a software RAID. Hardware RAID is a perfect technology when it comes to slow media like HDD or SATA or even SAS SSD. But when you try to deploy hardware RAID on NVMe, you face the problem that the connection goes to a PCIe bus, which is limited by 16 lanes, meaning that you can address only 4 SSD at a time at full speed. So you're limited by the design of the hardware RAID, and you're limited by the ASIC that is on the PCIe hardware card. So the alternative is to use a software RAID, and the obvious choice in a Linux environment is to use MD-RAID. The problem with MD-RAID is the way it creates a lock between the stripe and the core on the CPU. Like every software RAID, it uses the system CPU, and it creates a one-to-one lock between one stripe and the core, which is fine in reading, but it's extremely bad in a write operation, or when something goes wrong in degraded mode. So in that case, it creates additional copies and slow down the performance further. So the architecture of xiRAID is very different. So we use two main technologies in our classic implementation. We use AVX technology, which is available on every modern x86 CPU. And we combine it with our lockless data path. What does it mean? It means that we have a way to dynamically allocate the stripe to the available core so that we can distribute the load evenly across all the available cores on the CPU. And since we don't have a memory cache, this allows us to achieve a very even distribution of the load that we equal very high performance. So nearly the raw drive performance. So before we dive into the case study, a quick look into some performance number, because that's the main reason why people should deploy our RAID engine instead of open source MD-RAID. If we look at comparison with MD-RAID, MD-RAID in RAID 5 and RAID 6, it suffers a lot in performance. So we did a benchmark comparing our RAID 5 and 6 against MD-RAID in RAID 10, just to be a bit more fair with MD-RAID. And you see two bars for xiRAID. One is xiRAID Opus, which is a version of the code working in user space, which normally is positioned for a disaggregated infrastructure or virtualized environment. The beauty of the Opus version is that we can work also with the ARM CPU. So, for example, we validated Opus with the Bluefield 3 from NVIDIA. The classic implementation operates within the kernel, and by operating within the kernel, we expose a block device where you can mount a file system on top and to run the application. So if we look at sequential performance, there is no much differentiation that can be done. So with 24 NVMe PCIe Gen 5 in a single server, we were able to see 300 gigabytes per second, up to 300 gigabytes per second. But then when you start doing some write in sequential write, our performance in RAID 5 is about 2x what you can get with MD-RAID in RAID 10, or 50% better even with RAID 6 versus MD-RAID in RAID 10. And then the comparison in random is very unfair because we have multiple order of magnitude of performance improvement both in random read and random write. MD-RAID is not the only software RAID in the market. People are very familiar with ZFS or ZFS, depending if you are in Europe or the US. So we did some comparison. We did some, you can look on our website, there is a blog post, which is a very techy blog post, which will explain the limitation of RAID Z and RAID Z2 on ZFS. Basically, the limitation is that with ZFS on flash, you are limiting the performance by about 50% of the theoretical performance you can get with the NVMe drives. And in addition to that, you see in the chart, in the picture, there are spikes of load on specific cores. So we did by replacing the RAID engine within ZFS with our xiRAID, what we can see is 2 times better performance in sequential performance, much more balanced load among the CPU cores. And also we can add a higher level of protection because we support not just RAID 5 and 6, but any RAID level you might think about. Okay, so that was just to set the stage to explain what is our RAID engine. With this, let me hand it over to Markus, who will explain a real case study that we recently did.
Yeah, thank you, Davide. I hope you can all hear me fine. So now I would like to talk a little bit about one case study we did together with NAR at FAU Erlangen, so with University of Erlangen. So next slide, please. So what we did, so they have a cluster called Alex. That's a GPU cluster with some A100 and some A40 GPU nodes, usually used for HPC and machine learning. And for this cluster, they also needed some fast flash-based storage, especially for the machine learning users. So the initial plan was to purchase 7 NVMe servers. These are 2U servers with 2 sockets and 24 NVMe's each. So quite a bit of NVMe's. And initially they wanted to put ZFS on these servers and then use ZFS as their like NVMe-based storage solution. So they did this for a couple of months, and unfortunately, the performance was not that satisfying. So they were searching for alternatives, and we talked to them, or regularly talked to them, and thought about making a POC together with xiRAID and Lustre, and deploy this on one of the servers to see how it performs and compare to the previous ZFS solution. So one thing you have to keep in mind that this hardware was never purchased to like run Lustre and stuff. So this was purchased for ZFS. That's why also the hardware is not like a perfect match for the solution. We will come to better hardware in the next POC. But anyways, I think I just want to show that even with existing hardware, which might not be perfect for this solution, you can still increase performance by quite a bit. So, and especially the issue with these servers here is that we have a big network bottleneck. So we have 24 NVMe drives, but we only have a single 200 gigabit InfiniBand connection and a single 100 gigabit Ethernet connection. So that's by far not enough to fully utilize all the 24 NVMe drives in such a server. So, but anyways, we set up one server with a test setup, and you can see it here on the picture. So we have 24 NVMEs. So we used two RAID 6 with 8+2 for OST, Lustre OST. So that's 20 drives in total. And then the remaining 4 drives we set up in RAID 1 for MDT. So each server will then have 2 MDTs and 2 OSTs. And then, it's LDiskFS. So xiRAID for the RAID 6 and RAID 1, and then LDiskFS on top. And then we have the InfiniBand and the Ethernet connection, and we export Lustre via InfiniBand with RDMA support and via Ethernet as well, because as you see on the top left, the A40 nodes only have Ethernet, and only the A100 GPU nodes have InfiniBand. So on the next slide, you will see a comparison, and that here a big disclaimer, that's not an apple-to-apple comparison. Yeah, that's not like a perfect comparison, but we wanted to have like at least some numbers to compare before and after. So here we have 3 servers out of these 7 still running the old ZFS installation, and 4 servers are running the new xiRAID together with Lustre. So that's not fair at all, because it's like 1 server more for Lustre. And on top of that, the network is also different because ZFS is unable to use RDMA. We only can use Ethernet on ZFS. So the network is also a little bit slower compared to the InfiniBand network we can use on the Lustre installation. Yeah, so that's not like completely fair, but still, even if you have a look at the network limits, we still get numbers which are way higher, and not just because of the network limits, but also because of the underlying block device performance, basically. So yeah, as you can see here, it's only showing IOR easy for now. We are able to get like 60 gigabytes a second write and 84 gigabytes a second read with xiRAID and Lustre. And previously with ZFS, it was only like 10 and 21. But again, in the next like POC, we will have like a better, way better performance, because the hardware is just better suited for this solution. So like in summary, what does it show us? So first of all, we get like higher throughput as expected. We also get some more capacity for ZFS. The lowest, like if you still want to have high performance, you usually use replica, because it's like more performance than erasure coding. And then the lowest you can go is 2-way replica, and then you lose like half of your capacity. So with this solution, with 7 servers, it's roughly 580 terabytes. And with xiRAID and Lustre, we can utilize RAID 6, for instance, in this case. So we get some more capacity out of it. And then, of course, we are using Lustre, so we can use InfiniBand RDMA support. Next one, please. So, but maybe you noticed we only have 7 servers with 24 NVMEs each. So a single or 2 NVMEs can fail. That's not an issue. We have RAID. But if one of these servers goes down, we can't access the data on the server anymore, obviously, until the server is repaired. So because this is only a scratch-based file system, this was not like a requirement to have like fully high available solution. But obviously some want to have like also highly available servers, so they can still access the file system. So we will come to this later on, where we show you how to make this highly available. Yeah, and now I already mentioned that we had another POC because, again, the hardware was not perfect. We had a huge network bottleneck, but fortunately I got some better hardware to play with to deploy this solution to. So on the next slide, you will see how this looks like. Here we have 14 servers with a single socket system, so no NUMA shenanigans or anything, just a single socket. And then we have 2 times a Connect X6 NDR400 connection. So each server has roughly 100 gigabytes a second network throughput. So that's quite a bit. And then each server features 12 PCI-4 NVMEs with roughly 7 gigabytes a second read and 4 gigabytes a second write performance according to specs. And then again, we configured this with a similar setup. So each server has 1 MDT in a RAID 1 setup, and then the remaining 10 drives in a RAID 6 setup with 8+2. Again, with xiRAID 1 and xiRAID 6. So in total, we then have like 14 MDTs and 14 OSTs. And the clients are basically the very same servers. We just didn't use the NVMEs on the clients, basically. So, but it's the same single socket CPU, 2 NDR400 connections as network connections. And so everything else was the same. So I wanted to target the IO 500 10 node challenge with this system. So that's why it's like 10 clients and 14 servers, because in total I had 24 of those nodes. So here you can see again the solution, how it looks like. So 12 NVMEs in each server, 14 servers, and then the 10 clients all connected via 2 times 400 gigabit InfiniBand. So now, before we see the actual performance numbers, let's do some theoretical calculations on what kind of performance can we expect from such a system. So on reads, so the numbers you can see here, 6.7 gigabytes and 3.8 gigabytes a second, that's measured with FIO on a single drive. So because I wanted to get some like real life numbers and not just a spec sheet. So this is what I got with FIO locally, just a single drive benchmarking. Yeah, and then for reads, because each server has 10 drives in the RAID 10, so we can read from 10 in the RAID 6, so we can read from the 10 drives with 6.7 gigabytes a second, and then we have 14 servers. So in total, we have roughly 900 gigabytes a second read speed, theoretically. And then on the writes, we can't write to parity, so we have 2 parity, so we can only write to 8 drives. So in theory, we have roughly a little bit above 400 gigabytes a second write speed. Yeah, if everything is perfect. And then of course we have like some network layer on top, and then Lustre layer on top. So the closer we get, the better we are. So on the next slide, you can then here see the actual IO 500 10 node challenge result we achieved with this setup I just mentioned. So as you can see here, so please keep in mind these numbers here are in gigabytes per second, not gigabytes per second. So gigabytes a second is a little bit higher. So it's roughly 350 gigabytes a second for writes, and a little bit over 600 gigabytes a second for reads we achieved. So that's already pretty good for such a small system. And then if you have a look at all the MD test and metadata stuff, you can also see that the performance, can you go one back, please? You can see that the performance of the metadata is also really high. And in total, we got a score of roughly 250 IO 500 score, which basically is right now with the current released list the third fastest Lustre system in the 10 node research category, which is for just like 14 servers doing the actual Lustre IO pretty good, I would say. And then on this slide here, you see a different benchmark. It's called LBencho. Some of you may know it. It's similar to IOR. But this allows us to see the actual throughput, like right in the middle of the IO workload, and not only just once, like all the threads finished, and then we have an average across the whole time frame. So this shows us what the system is really capable of doing during doing IO. And here we can see the write speed is roughly the same, 350, but for reads we reach up to 800 gigabytes a second. And now if we compare this number again to our theoretical limits we showed at the beginning, we can see that we are able to reach a read efficiency of roughly 90% and the write efficiency of roughly 82%. So I think that's a really good usage of the underlying hardware if you keep in mind that this is also InfiniBand and Lustre on top, and then xiRAID, and then the block device, and we get these numbers across to the clients. So I think that's a really good result, and especially without any additional special hardware, just the CPU doing the actual I/O. And now here I have some more interesting results. I also benchmarked a single server, so that's basically a single OST with 10 drives. So there I got 29 gigabytes a second write and 59 gigabytes a second read speed, which then, if you divide it by 8 for writes and by 10 for reads, is roughly 3.6 gigabytes per drive write speed and roughly 6 gigabytes a second for reads, which is very close again to the spec of the device. So it's really easy to really utilize the full hardware performance you have. And then below, you can also see a result using just a single Zen 4 core, because Davide mentioned xiRAID is basically using AVX instructions to do the parity calculations. So obviously it needs some CPU cycles, but the code is really super efficient because, as you can see, if we just use a single Zen 4 core, and that's even with single Zen 4C core, so that's a compact core with less L3 cache, and that's a little bit slower than your usual Zen 4 core usually. With just a single core, we already get 15 gigabytes a second write and 45 gigabytes a second read speed. So for this setup here, to fully utilize a single server, we basically just need 2 out of these 32 cores to get the full performance for xiRAID. So it's really, really low performance overhead you have because of xiRAID, compared to other solutions especially. So now I also want to share you some Lustre and IO 500 tuning tips. So because I did this 10-node IO 500 challenge, along the way I also discovered some things to improve performance on the Lustre side. So this, and also IO 500. So this I want to share with you. So first of all, and this is usually just important if you do like something like a 10-node challenge, or if you don't have too many clients, you should use POSIX or Direct, because if you don't use POSIX or Direct, you just lose a lot of performance because of the Linux page cache on the client. And with Direct IO, you just directly write to Lustre without using the page cache. So that's usually way faster, especially for benchmarks. But Lustre 2.16 will also have a very neat feature. So 2.16 will come in Q4 this year, usually. And it's a feature called Hybrid IO, which basically enables Lustre to automatically switch to direct IO if you are doing aligned IO. So if you do like 4 megabyte block size or stuff like this, then Lustre can automatically switch in the background without you noticing, switch to direct IO to do the IO, and which is then faster for bigger block sizes. So then you wouldn't even need this POSIX or direct flag in Lustre 2.16. And then below here, you see the IO 500 shell script settings for striping and so on. So this is basically the defaults you can see in the script. So there are comments for Lustre tuning, and that's basically the default. So there's nothing special about it. It's just like striping metadata across all MDTs, using data on metadata for the MD test stuff, and for IO hard to do some overstriping for better performance. How many applications middleware? There's a question in the chat. How many applications use really direct? Oh, not a lot. So that's just usually just useful for benchmarking to really show the full system performance. Because if you would have like 100 clients, it wouldn't matter. You can use buffered IO and you would get the same performance. But if you only have 10 clients, your clients are basically the limiting factor if you are using buffered IO. So that's why for such a small number of clients, direct IO is better to really show the actual file system performance and not some client page cache performance, basically. So this one here shows you some Lustre tunings are applied for this IO 500 run. So you don't have to apply all of them, but some might be useful for you as well. So first of all, you can enable 16 megabyte bulk RPCs. So by default, Lustre is using only 4 megabytes RPCs. So you can increase this up to 16. And this allows you to utilize the network a little bit better because you can send bigger packets across the network. Then also you can allow more RPCs in flight, which again also helps utilizing the network better. Then another setting you can set, and you don't have to, it comes with roughly a 20% performance hit. So Lustre by default is doing checksums for all network communication. But usually you have ECC memory, and InfiniBand is doing checksums on its own anyways. So usually you don't need this. But if you just want to be very sure, leave it enabled. But if you don't care too much, you maybe can disable it to achieve some better performance. And then a little bit strange thing is that if you limit the number of locks a single client can have in Lustre, you get way better metadata and IO hard performance. I'm not sure if this is a bug. So by default, Lustre automatically scales the number of locks a single client can have based on available client memory. And so for like 500 gigabytes of memory, this can reach like million of locks. But it looks like, especially for IO 500, this slows down some operations because maybe the lock table is just too big then. So if you lower this, you actually get better performance. So, but I used a development Lustre 2.16 development build for these tests. So maybe this is also just still a bug in 2.16. There's another question in the chat. Does xiRAID provide a local Linux block device like xiRAID? Yes, exactly. It's basically providing a block device like xiRAID, and then you can just use it. And it's also for NVMe over Fabric, yes. So you can use it locally or with NVMe over Fabric devices. And now the last slide here, LNet tunings. LNet tunings are pretty much default. I only increased the credits a little bit because we have quite a fast network with like 2 times 400 gigabit. So yeah, just the credits were increased a little bit for this installation.
Okay, so Markus mentioned earlier that the implementation at FAU University is for Scratch, so there is no high availability in that specific implementation. But for some other deployment, you might need high availability. And our team has been working on integrating xiRAID Classic 4.1 with Pacemaker so that we can support HA cluster over NVMe drives. So there are two ways you can implement high availability with our RAID engine. So you can do it on a storage bridge bay dual node server. So those are servers made of two independent nodes, compute nodes, connected to share NVMe drives. And actually, we have one example in the following slide. There are few vendors, not many vendors, producing those type of servers. Celestica, Viking, AAC, and we know Supermicro is coming to the market as well with their own server. And the other way to do high availability is to use an external eBOF, Ethernet attached JBOF, like the Data24 from Western Digital. So in current implementation, we support high availability on the eBOF when it's connected to two independent servers. But by the end of October, we will release 4.2 that will also support multi-node cluster. So it's around the corner, and we're looking for a leading customer who want to experiment a multi-node cluster on NVMe.
Yeah, and to show you some like real life example, what kind of hardware you could use nowadays to build such a solution, the highly available solution based on xiRAID with Lustre, or in the end you don't have to use Lustre. I mean, you can use anything else, but we just tested with Lustre because we got like the best performance with Lustre. So for instance, here this Celestica SC6100 system. It's a 2U box with 2 servers inside, and then you have like a backplane with 24 NVMEs, and these NVMEs are attached to both servers. So these are PCI 5 slots, and then you have a PCI 5 by a 2 connection to each server. So for this, you need dual port NVMEs. So yeah, make sure to have like dual port NVMEs, and then you can use a server and have like basically fail over the drives or the RAID with the drives to one or the other server. If like one server dies, you just set up pacemaker and co-sync, how you would also do it with a normal like SAS-based JBOD or something like this, where you have like 2 servers and then a JBOD with hard disks or something like this. And then with Lustre, you would also set up pacemaker and co-sync to fail over between both servers. And that's pretty much the same. You just have everything in like a 2U box, your drives and your servers. And then for instance, like an example configuration of this server could look like you have 20, 30 terabyte disks, 30 terabyte NVMEs. So for instance, the Phison Pascari NVMe, which has quite nice specs with like 14 gigabytes a second read and 7.5 gigabytes a second write speed. So that's a pretty fast PCI 5 based dual port NVMe you could use. And then the remaining 4 slots, again, you could use for your metadata devices. So you can put in some smaller and even faster PCI 5 dual port NVMEs for metadata, for instance, like 6.4 terabyte drives in this example. And then on this example, you would get roughly half a petabyte of all flash Lustre in this like 2U box with xiRAID on top with 2 times RAID 6 and then the RAID 10 for metadata. And then one thing to mention is that you would then split your NVMe devices in 2 halves, so in 2 namespaces. One namespace would be for server 1 and the other namespace would be used by the second server to really get the full PCI Express throughput, because each server has only a by 2 connection to each NVMe. and PCI 5x2 is only doing roughly like 7-8 gigabyte a second. So to really get the full read performance out of the drives, you need like 2 namespaces, and then each server will access 1 namespace, and therefore each server can access the same NVMe drive at the same time, basically. So in total, you would then have 2 MDTs and 4 OSTs out of this 2U box because of the namespaces, and then failover with pacemaker corosync. And the performance expectations for this specific example here would be roughly 200 gigabytes a second read and 80 gigabytes a second write speed for a 2U box and half a petabyte of Lustre. I think that's quite a good performance. And the nice thing about Lustre is that you can have like different network interconnects and also mix different network interconnects. So each of these servers has 4 PCI 5 slots. 2 of these slots are by 16 slots and 2 of them are by 8 slots. Therefore, you in like a to fully utilize the network throughput, you could, for instance, have like 2 times NDR 400 per server, and then 2 additional NICs with 100 gigabit Ethernet, for instance, with dual port 100 gigabit Ethernet. So in total, you could have 200 gigabyte a second InfiniBand throughput across both servers and roughly 100 gigabytes a second Ethernet throughput across both servers, and then you could export your Lustre to Ethernet and InfiniBand at the same time. Yeah, and you could also use OmniPass or Slingshot, whatever. Everything, for instance, Lustre supports, but you are really like flexible in the choices of network connections, basically, and you can like scale down and up your network connections based on your needs. So yeah.
I see there is a question, is xiRAID a kernel driver? If so, then which kernel it requires to work? Yeah, okay. The answer to this question is that we have 2 versions of our xiRAID implementation. We have xiRAID Classic, which is a kernel module working under a Linux kernel. We support many different distributions of Linux. If you go on our website under the documentation page, you have all the supported distribution. And that's for xiRAID Classic. But we also develop xiRAID Opus. Opus stands for Optimized Performance in User Space. And in this case, we started from the SPDK libraries, and we modified the libraries. We implemented our calculation libraries, our control plane, our volume management, and multi-thread vhost. And in this case, we remove the dependency from the kernel, and we operate in user space.
Yeah, but maybe to add on this, this solution, the Opus, is right now not able to give a block device to Linux. So if you need a block device, you right now, this might change in the future, but right now you need to use a classic version, which is the kernel module. So in fact, it's a DKMS-based kernel module, so it will automatically also like build when you update, or rebuild when you update the kernel. And yeah, so similar to like your Lustre kernel module, you could say.
Yeah, that's correct. The Opus version, we position it only for NVMe over Fabric, over RDMA or TCP, or a virtualized environment, as you can access it through virt.io. Okay, I think that was the last slide. If you, with your phone, if you go on this QR code, it will prompt you to a blog post that we just released. It's another very technical document that will explain you step by step how to set up high availability within Lustre with xiRAID and pacemaker. We will be releasing the same document shortly with the BGFS as well. So it's a matter of days, and we will make the same document available for the BGFS users as well. And with this, I believe we reached the end of the presentation. I think we can open up for more questions. And while we wait a question, I probably anticipate one of the questions